Assume there are two objects. Okay, we'll consider two spheres first, but the ideas that we discuss are applicable generally to all kinds of objects. Okay. Consider these two sponge balls. Fine. Assume they are both moving to the right. Let's say one is going with a velocity u1, the other is going with a velocity u2. Can one of you tell me the condition for them to collide? Like the condition between u1 and u2 such that they collide. Will they collide irrespective of the values of u1 and u2, or should there be any relation between them or a condition between them?
So U1 greater than U2.
u1 should be greater than u2, correct? Okay, so assume that is valid, u1 greater than u2. Fine. Now see, I have conveniently chosen both of them to be moving in the same direction. That need not always be the case, but you'll understand after the derivation and all is complete, you'll understand that even if objects are not actually moving in the same direction, you can write their velocities in the same direction and solve problems. Okay, you'll understand how to do that. So suppose u1 is greater than u2. Now let's name them as A and B. So it's like A is chasing B, A is behind B, but they are on the same straight line. So definitely they will come into contact at some point. Okay. Imagine A and B just come into contact. Why is this getting selected? Okay, see, A is moving faster than B, so definitely A will catch up with B. Let's say they just come into contact somewhere ahead along this same straight line. For now, what we are discussing is called one-dimensional collisions. Next, we'll discuss 2D collisions also. Okay. Once the spheres or the balls come into contact, what force do they exert on each other? Once they come into contact, what force do they exert on each other?
Normal force.
Normal force. Okay. So A will exert a normal force on B that will be to the right. And B will exert a normal force on A that will be to the left. Are these two an action-reaction pair or not? Answer quickly. Are these two an action-reaction pair or not?
They are.
They are. Okay, fine. So due to the normal force, B's momentum will get disturbed. And due to the normal force, which is an external force or force for A, A's momentum also will get disturbed. But if you consider A and B together as one system, can one of you tell me how much is the net force on this system? A and B together as one system, how much is the net force on it?
0.
Zero. Fine. And if net force is zero, we know that conservation of linear momentum is applicable. So usually in collision questions, we will definitely apply conservation of linear momentum unless there is an impulsive external force acting on the system. We'll look at situations like that also. For now, the net force on this system is zero, so you can apply linear momentum conservation. But let us look at the different stages of collision first. Now, this is just the beginning of the collision. Okay, so it's like stage one. Fine. Who is moving faster? A is moving faster than B. Because A is moving faster than B, this collision will happen, and due to the normal force, you see what happens. B was moving to the right, normal force is also to the right, so B's velocity will increase. A was moving to the right, but normal force on A is to the left, so A's velocity will decrease. Okay, so let's say initially, I'm taking some rough values, okay? Assume initially A was moving with some speed 20 meters per second and B was moving with 10 meters per second. Okay, this is just the beginning of the collision. Here the speeds are still 20 and 10. But because A is moving faster than B, some compression will occur. Okay, so at the next instant or the next stage of collision will be something like this. Normal force will keep acting between them, but deformation will occur now. Okay, so what happens? Sphere A will get compressed a little bit. Sphere B also will get compressed a little bit. Situation will be like this. And what would have happened to the speeds of A and B? A speed will decrease, B speed will increase. But it's not necessary that A becomes slower than B immediately. A speed is initially 20, B speed is 10. Okay, if their masses are equal, then you can see something like this happening. A speed maybe changes to 18 and B speed becomes 12. So A is still faster than B. Okay, speeds are in the process of decreasing. Okay, we are looking at collision in detail. Fine. So as the collision progresses, this is like stage 2, speed of A decreasing and speed of B increasing. But still A is moving faster than B. So what will happen? Some more compression, some more deformation will occur. Okay, and they will keep exerting normal force because A is still moving faster than B. No, so A will push B, B will push A in the opposite direction. Normal force will continue to act. Okay, so this is like stage 2 of the collision. Deformation is happening. Okay, and next you will have stage 3. As long as A moves faster than B, they will keep getting deformed. Okay, they will keep getting compressed. But A speed goes on decreasing, B speed goes on increasing. At some instant, their speeds will become equal. Okay, let me bring all this down. Okay, there will come one instant where the velocity of A becomes equal to the velocity of B. Definitely, because A continuously slows down, B continuously speeds up. So at one instant, their velocities will become equal. Okay. Actually, the compression, I should not show it this way. Compression happens where they are in contact with each other. You understand that anyway, because basically what happens is, suppose it's a sphere initially. When it is getting compressed on the right side, you will see something like this happening. Like it will go out of shape on the side where it is in contact. Okay, so it will become somewhat like this. Okay, but here I just, uh, you know what I did? I just adjusted the size of the image. Let it be. So as long as A moves faster than B, the deformation will keep on happening. When will deformation stop happening? When their velocities become equal. Because now A is not moving faster than B, so A won't be trying to compress B anymore. Okay, they won't be coming close to each other anymore. Two objects will come closer and closer only when their relative velocity is non-zero. Okay, velocity of one relative to the other is towards this second object. But now once their velocities become equal, their relative velocity is zero, means they are neither approaching nor getting separated. Okay, so this is the third stage. That's the stage of maximum deformation. Okay, it's very important to visualize all this happening during a collision. Fine. So I'll erase these velocities. So you know collision happens only when a velocity of A is greater than velocity of B. At maximum deformation, their velocities become equal. That is important. Is equal to VB. Okay. Till then they will exert normal forces on each other. Now tell me, what do you think will happen after maximum deformation? Try to guess. Like their velocities have become equal. Will they still be pushing each other or will they stop pushing each other? During all these stages, the net force is zero. After maximum deformation, when their velocities become equal, will they continue pushing each other or will they stop pushing each other? Okay,
They will stop pushing each other.
okay, when I saying they'll stop pushing each other, we'll see. Let's consider the situation that we took in the last class, tennis ball striking a ground. Okay. Now, see, the first image is when the ball just comes into contact with the ground. It still has velocity in the downward direction. It just touched the ground. But the moment it touches the ground, it experiences a normal force like this, which will oppose this velocity and it will slow down the ball. The ball will come to rest at one instant. That is this instant. Okay. The ball undergoes some compression and comes to rest. After that, what will happen? Will the floor still exert a normal force on the ball, or that's all? Once it comes to rest, there won't be a normal force acting on it. Aishwarya, what do you think? When the ball is in the compressed state at rest, will there still be a normal force from the ground or normal force will stop acting?
Yes, sir. It will be normal.
Okay, how do you justify that? Why do you say there will still be a normal force?
Yes, because the ball and the ground is in contact.
Yeah, they are in contact. Okay, because there is contact, there is a normal force, you are saying. Okay. And yeah, here it's a case of gravity. Gravity being present. So yeah, you have to consider weight of the ball and all. What you're saying makes sense. But Aishwarya, do you think the normal force here simply balances the weight of the ball, or is it more than that? Anyone? Pawan, what do you think?
More than mg.
More than? Can you justify that in any way? How can you say it is
Sir,
more?
sir compression అంటే ఫోర్స్ డౌన్వర్డ్ ఫోర్స్ ఎక్కువ ఉంది సార్.
Okay, okay, that's one way to say. Correct only, correct only. Yusuf, what do you say? Should the normal force just balance the weight of the ball when it comes to rest, or do you think it will be more than the weight of the ball?
So more.
Okay, can you give any justification to that? Why do you think it is more? Okay, listen, all of you. What Pawan said is correct only. That's that's one way to explain that normal force will be more than mg. What he said is that the ball is in a compressed state. But see, a tennis ball, when you squeeze it and release, it will come back to its original shape. No. Now this ball, if it wants to, if it has to come back to its original shape, then it needs some space. Okay, it's in a compressed state. It will expand now. It will relax now. In that process of relaxing, it will press the ground harder. Okay, if only its weight was acting on the ground, then normal force would have been equal to mg. But now the ball wants to relax. It's in a compressed state. No, it's like a compressed spring. It wants to come back to its original shape. Okay, tennis ball naturally tries to become a sphere when you remove the force acting on it. Okay, so in the process of trying to become a sphere again, it will, like, you imagine this as the ground. Okay, let's say this is the compressed tennis ball. Then what will happen? It's like a spring. It has to relax. So in that process, it will hit the ground. It will push the ground further downwards. So normal force will be more than mg. That's one way to explain. And you can explain based on what happens to the ball also. See, in that compressed state, ball is at rest. Okay. But it doesn't stop there. No, it rebounds. If normal is just equal to mg, then net force is 0. What will help the ball go up again? Okay. The ball has to rise up. We know it rises up. Okay. It comes back to its original shape and rises up. So it's rising up means there is a net force in the upward direction from that resting position. There's a net force in the upward direction means normal force should be more than mg. Okay. So it all depends on whether the ball is trying to come back to its original shape or not. Now, instead of the ball, if you take a lump of clay, okay, let's visualize it in today's notes itself. Assume this is the floor, okay, and just a moment. Okay, never mind the color. Let's say you drop a lump of clay, okay, wet clay, onto the floor. Okay, when that lump of clay comes into contact with the floor, situation will be like this. Floor will exert a normal force, it will get deformed, becomes maybe somewhat like this. Okay. There will be a normal force acting on that lump of clay, but we know that that lump of clay will not rebound when you smash it against the ground. Okay. That means once it comes to rest, it undergoes deformation, comes to rest. Once it comes to rest, the normal force is equal to mg. Now, why is it not rebounding? Because a lump of clay naturally won't have a tendency to go back to its original shape. It won't even try to restore its shape a little bit. Okay. So if it is not trying to get back to its original shape, it won't push the ground harder than its weight. Okay, so it won't rebound. Fine. So whether two objects, like in this case, I can tell there's mg acting, so normal force is equal to mg. No extra normal force arising from or arising due to a tendency to get back to original shape. Okay, that extra normal force will not act in this case. Here, there in the case of tennis ball, okay, ball naturally tends to come back to its original shape. No, based on the material with which it is made. So here, normal force is greater than mg. Where is that extra normal force coming from? From the tendency of the ball to get back to its original shape. So my question actually was whether the objects will continue exerting normal force even at maximum deformation. Okay, their velocities have become equal. A is not moving faster than B, so A has no reason to push B now. Due to velocities, A has no reason to push B. But you can see that A and B are both in a compressed state. If they want to get back to their original shape, now see, if A wants to become a sphere again, it needs space around it, right? Similarly, if B also wants to become a proper sphere again, it needs space around it. So in that process, if they have a tendency of coming back to their original shape, they will continue exerting normal force. But suppose these two were two lumps of clay, even when they collide, they undergo deformation, they won't have a tendency to get back to their original shape. So they'll stop exerting normal force. Okay. So this is the most important thing in collisions. What happens after maximum deformation? Up to maximum deformation, stages 1, 2, and 3 are common in every collision. Okay. Even if it is like two steel balls colliding with each other or a steel ball hit against a floor or a wall. Okay. Even steel will undergo a little bit of deformation. Even, okay, little bit of your chemistry knowledge I will test. What is the hardest material on earth? What is the hardest or strongest material on earth?
Diamond, sir.
Diamond, correct. Okay, on a hardness scale, it's called Mohs scale, I think, MOHS. Okay, diamond is given a rating of 10. Okay, it's the hardest material known to humans, fine, and that we find on Earth actually. Even a diamond will undergo a little bit of deformation when it hits something. We may not be able to notice it. Okay, like very rigid objects, like you can take a steel bottle. Okay, you gently hit it against something. You may not be able to notice a deformation in the steel bottle at all, but it will happen. Even a plastic pen, okay, you hit it like this. You may not be able to see it getting deformed, but at the molecular level, some slight disturbance will happen. Okay, so these stages are common in any collision, howsoever hard the material may be. Deformation will occur at one stage, maximum deformation will occur. Okay, after that, whether they try to get back to their original shape or not, based on that, we can tell what will happen after maximum deformation. And the tendency of an object or a material, I should say, the tendency of a material to come back to its original shape is what is called its elasticity. Okay, I want you all to note down this definition. The tendency or ability of a material to get back to its original shape after being deformed. Okay, you can also define elasticity like this. Okay, this is one definition. Another definition is the resistance to deformation. If a material resists deformation, we say it is elastic or more elastic compared to another one. Fine. Now you all tell me this. Out of steel and maybe rubber, which is more elastic? Type your answer in chat. Like from your everyday knowledge, you tell, and read this definition also carefully. Okay. Out of these two materials, which is more elastic? Think and type your answers quickly. I got only 2 answers till now. Okay. I got 3 answers as steel and 2 as rubber. Steel is the correct answer. Steel is more elastic than rubber. See, in everyday usage, no, materials which stretch more are called elastic. Okay, like rubber. What else? Sponge. We call them. We say they are elastic. But actually, in the scientific definition, okay, or based on the scientific definition, materials which resist deformation, which resist stretching, are said to be more elastic. Like, see, is it easy to stretch a wire of steel or a wire made of rubber? Wire made of rubber is easier to stretch. Means steel is offering more resistance to deformation. Means steel has a greater tendency to maintain its shape than rubber. Okay, that is why steel is said to be more elastic. Stretchability of rubber is more, but elasticity of steel is more, okay, than rubber. So that's why it's important to remember what elasticity means. Okay, don't Consider the everyday definition that we use, okay, or everyday meaning that we take. In daily life, if material is more stretchable, easily stretchable, we say it is elastic, but no, that's not the case. If anything has a greater tendency to maintain its original shape, that is said to be more elastic. Okay. So what happens after maximum deformation depends on the elasticity of the materials which are undergoing collision. If they don't have any elasticity, okay, materials having zero elasticity are said to be plastic. Okay, completely plastic, or you can say perfectly inelastic. Fine. So elasticity and plasticity are opposites of each other. Elasticity is the ability of an object to get back to its original shape. Stronger the ability, more the elasticity. Plasticity, on the other hand, is the inability of an object to get back to its original shape when deformed. Okay. Just a moment. So in every collision, the two colliding objects will definitely come to a stage of maximum deformation where their velocities will become equal. And you see, it is like this change in velocity and all is happening due to the normal force acting between the two colliding objects. Here in this diagram, I've already drawn a straight line. The objects are moving on that straight line, and normal force is also acting along that straight line itself. The line along which normal force acts during collision is called line of impact. Okay, so this line here is called line of impact. Okay, in this case, it's obvious this is the line of impact, but in some collisions, you will only have to find out the line of impact. For example, that tennis ball case, if you take, okay, you know how the normal force is acting. No, normal force acts vertically because the floor is horizontal. Then this vertical line becomes a line of impact. So the line along which the colliding objects exert normal force on each other is what we call as line of impact. It's very important to visualize that line to solve problems or while solving problems based on collisions. Okay. So line along which the colliding objects exert normal force on each other. Now in this case, in the example that we are working on, the objects are moving along the line of impact itself. Okay, this kind of collision is called a one-dimensional collision. Both objects will be moving along the same straight line before collision, during collision, and after collision also they'll stay on that straight line only. It's called a one-dimensional collision. Suppose the objects go away from this straight line, or initially they were not on the same straight line, not moving on the same straight line, then it's called an oblique or a 2D collision. We'll come to those. We'll discuss those cases later.
Sir, can you show the line of impact part?
Okay, 1 second. The line along which colliding objects exert normal force on each other. Okay.
Yeah, sir, you can scroll.
So during this process, as the deformation occurs, the net force on the two colliding objects is zero. So linear momentum conservation is applicable. Just a moment. Here we have taken an example where both the objects are moving in the same direction. And u1 greater than u2, that is when the collision will take place. Now let's solve one problem based on this. Okay, let's say, and let's call them as A and B itself. This is A, this is B. A's mass assume is some 40 grams. B's mass, let's say, is 20 grams. Suppose A is moving with a speed 10 meters per second. B is moving with a speed 5 meters per second. We know collision will occur definitely. A speed will decrease, B speed will increase till they come to a common speed. That is definitely going to happen in any collision, irrespective of the materials with which they are made. Fine. Okay, first question. Calculate their speeds at maximum deformation. And then calculate the kinetic energy lost from the system, means from both of them, okay, during deformation. Solve very carefully. First, imagine the stage of maximum deformation. At maximum deformation, their velocities become equal. Whether the normal force acts or not after that stage depends on the nature of materials, but their velocities will definitely become equal. That much we know. Just a moment, let me. Calculate that common velocity. Any answer? Okay, which concept will you apply to derive that final velocity?
Conservation of linear momentum. Sir.
Conservation of linear momentum. And generally, how do we write the equation for conservation of linear momentum? Listen, all of you, any quantity, if it is conserved, no, then its value at one instant. So initial momentum of the system at the initial instant should be equal to momentum of the system at the final instant. And the system here includes both these spheres. Okay, for individual spheres, momentum is not conserved because the normal force acting on each sphere is an external force. But both of them together, if you take, then the normal force becomes internal to the system. It won't contribute to the net force. Okay. Solve this carefully. Yusuf, what is the formula for momentum of an object? Aishwarya, what is the formula for linear momentum of an object?
So mass into velocity.
Mass multiplied with velocity. Okay. Do this quickly. So initial momentum of the system will be mass of A multiplied with initial velocity of A plus the mass of B multiplied with the initial velocity of B. And final momentum of the system will be mass of A multiplied with final velocity of A plus mass of B multiplied with final velocity of B. Finally, this velocity and this velocity are equal. At the stage of maximum deformation, their velocities along the line of impact will be equal. You can make use of that. Make it fast. Okay, Rishi, tell me, how much is the initial momentum of this system?
Sir, 500.
500 watt. Okay. So 40 into 10 plus 20 into 5, but 40 and 20 are in grams. So convert it to into kgs, you'll get a factor of 10 power minus 3. 40 grams is 40 into 10 power minus 3 kg. So you substitute all that, it will become 500 into 10 power minus 3 kg meter per second. Okay. 40 into 10 into 10 power minus 3, that's 400 into 10 power minus 3, plus 20 into 5 into 10 power minus 3, that's 100 into 10 power minus 3. Add them, it becomes 500 10 power minus 3. That's the initial momentum of the system. Finally, we don't know their velocities. Let's call that common velocity as v. Okay, listen to this carefully, all of you. This is how you are supposed to solve problems. Assume that common velocity is v, then the final momentum will be ma into v plus mb into v. You can take the v common. Okay, if you do that, then the final momentum effectively can be written as ma plus mb multiplied with that velocity. Okay, ma plus mb becomes 60 grams, that is 60 into 10 power minus 3 multiplied with v. So this becomes 60 into 10 power minus 3 multiplied with v. Now equate the initial and final momentum. That's all. So from momentum conservation, initial momentum is 500 into 10 power minus 3 should be equal to final momentum 60 into 10 power minus 3 into v. The 10 power minus 3 factor will get cancelled. You get v as 500 divided by 60 meters per second. 50 by 6, that's 25 by 3. Close to how much? 6 point, not 6, sorry, 8 point, maybe 8.3. Okay, something in that, something around that. Okay. Observe this carefully. We got 8.3 meters per second. A was initially moving with a speed of 10 meters per second. B is moving with a speed 5 meters per second. The moment they come into contact with each other, okay, they start exerting normal force on each other. So due to the normal force, A speed decreases, and due to the normal force, B speed increases, and A speed comes down to 8.3, B speed increases or goes up to 8.3. That is when their velocities become equal. Okay, that is what happens during maximum deformation. Is this clear to all of you? Any doubt in this? Yusuf, did you understand? No response. Okay, Vanilla, did you understand?
Yes, sir.
Okay, we just applied linear momentum conservation and we got their final speed. Okay, now we need to find out the kinetic energy lost from the system during deformation. How do you calculate loss? Initial value of the quantity minus final value. So initial kinetic energy minus final kinetic energy is what we need to do. Initially 40 gram was moving with 10, 20 was moving with 5. So initial kinetic energy, we can write it like this: half mass of A is 40 into 10 power minus 3 into V square is 10 square, plus half mass of B is 20 into 10 power minus 3. I am trying to express everything in SI units. So 20 to 10 power minus 3 multiplied with 5 square. That's the initial kinetic energy of the system. And final kinetic energy, finally, because they are both moving with the same speed, final means at the instant of maximum deformation, their speeds are equal, no? So what I'll do is I'll take the entire mass together, half into 60 into 10 power minus 3. And what's the speed? 50 by 6, that is 25 by 3. I'll square it. Okay, so this is all initial kinetic energy minus this is all final kinetic energy. You do that, you'll get the loss in kinetic energy. Not very difficult, it can be solved, and you will get this as a positive answer. Okay, loss is positive. That means kinetic energy is decreasing during deformation. Okay, how do we justify this? Can one of you tell me what force caused this decrease in kinetic energy? We know for kinetic energy to change, some force has to do work kinetic energy theorem. Okay, try to guess what force could have caused this decrease in kinetic energy during deformation.
Non-conservative force, sir.
No. How can you tell it is non-conservative? Conservative forces also can decrease kinetic energy. They'll convert it to potential energy. Non-conservative forces will convert it to other forms of energy. Okay, so you can't say whether it is conservative, non-conservative, but which force is it? I mean, I'm not asking the nature of force, but where is that force acting? Like, I mean, which force acting on the system did this?
An internal force.
Correct. Internal forces within the objects. That is what causes this loss of kinetic energy. Let us discuss this point in detail. See, these things, these finer details you won't find in textbooks and all, but you need to understand all this. Kinetic energy is decreasing. That means change in kinetic energy is negative. Loss is positive. Loss is initial minus final. Change is final minus initial. That will become negative. And from work kinetic energy theorem, we know that work done is equal to change in kinetic energy. Now, change in kinetic energy is negative. That means work done on the colliding objects is negative. Now, Aishwarya said internal forces must have been doing this. There's one more force also. There is normal force acting. I mean, see, for the system, normal force is, yes, an internal force. Okay. But there are forces within each sphere also. Inside that yellow sphere, when you compress it, there is a force acting inside that sphere, which is not the normal force coming from B. Intermolecular forces inside A itself will be there. Okay. And same with B also. B has forces inside itself. Okay. Not just the normal force coming from A or exerted by A. Fine. It is those internal forces that we are talking about. Forces acting inside the object A and inside the object B. Those are the ones which do this negative work. Okay, let us discuss this in detail. Now see, these two are solid objects or maybe semi-solids also, but they have slight tendency. They have their own shape originally. Just a moment. Okay, consider an object, any object, even if it's a lump of clay, that's fine. I'll consider this toy. Okay, this puppy toy that I have. Now tell me, if I want to deform this, should I exert a force or it will get deformed on its own? If I want to deform this toy, should I exert force on it or it will get deformed on its own?
We should exert force, sir.
It has a tendency to maintain its own shape, right? If you want to change its shape, you have to exert some force, okay, and squeeze it like this, or maybe stretch it like this. You'll have to exert a force. Why you have to exert a force to deform an object is because intermolecular forces will be opposing what you are doing. Okay, see, it is the intermolecular forces only which are helping it maintain this shape. Chemical bonds, whatever is there, they are helping it maintain this shape. So to change that shape, you have to exert a force. And when you are exerting a force, you can feel the opposition to your finger. Like, see, if you are exerting a force on the toy, the toy is exerting a force on you. Fine. Okay. Now suppose I try to compress this like this. Fine. I am exerting, or my fingers are exerting, an inward force. Tell me, what is the direction of force exerted by intermolecular forces? Is it outward or is that also inward? Rishi, what do you think? When I try to compress it by exerting a force inwards like this, the force that the molecules inside are exerting on my fingers, is it outward or is it inward?
Sir, it should be outward.
It is outward. Okay. To oppose that only, to overcome that only, I have to exert an inward force like this. Okay, so there are outward forces acting when I try to compress it like this. Now look at the kind of deformation that I'm producing, or look at the displacement that I'm producing in the particles. That when I squeeze it like this, the displacement is inwards, but the internal forces are acting outwards. Force is acting outwards, displacement is inwards. What is the work done by internal forces? Negative. Okay. Whenever an object is compressed, irrespective of whether it has a tendency to get back its original shape or not, if you are compressing an object, okay, if you are compressing an object, internal forces will be doing negative work. Okay. And if they are doing negative work, they will cause a loss in kinetic energy. And that is what happens during deformation here. Can you all see the screen?
Yes, sir.
Huh. So see, deformation will definitely occur whenever a collision occurs. And during deformation, internal forces will definitely do negative work. It is compulsory. You cannot change that. Okay, that is natural. So I'll write that statement here. In any collision, during deformation, internal forces do negative work. And if they are doing negative work, that means kinetic energy of the system definitely decreases during deformation. We are only talking about the deformation stage as of now. Okay. So kinetic energy of the system decreases during deformation. Fine. And in that question also, that is what we found. We found the final velocities of them at maximum deformation, and you find out the loss in kinetic energy. Loss is positive, means kinetic energy has decreased. In every collision, it will happen. Even in that ball striking the ground case, when it just comes into contact, the ball was moving, no? Maybe it was moving with some velocity like 20 meters per second or something. It depends on the height from which it is dropped. But as it gets deformed, the ball slows down, slows down. At one stage, at maximum deformation, it comes to rest. Means it has lost all its kinetic energy. Okay. If restoration happens, that kinetic energy will come back. But it depends on the extent of restoration and all. But during deformation, kinetic energy loss will definitely be there. Loss will definitely happen. Okay. Now, based on whether the objects have a tendency to come back to their original shape or not, we define three different types of collisions. Okay. So up to maximum deformation is common in any type of collision, irrespective of the material. What happens after maximum deformation depends on the extent to which the material gets back its original shape. Okay. So now we'll discuss the types of collisions. First, perfectly inelastic. Can one of you tell me the meaning of perfectly inelastic?
Sir, there is no resistance to deformation.
No resistance to deformation, no tendency to get back the original shape. Okay. So perfectly inelastic means the colliding objects have no tendency to uh, get back to their original shape or restore their original shape. Fine. Let's consider that instant of maximum deformation where the velocities of the colliding objects have become equal. Till there, it is common in every collision, as I said. What happens after that is what we are discussing now. Why did it come like this? Okay, never mind. Okay, so let's say they have come to this stage of maximum deformation. Let's visualize the line of motion also, line of impact. But 1 second. Okay, once they get deformed to the maximum possible extent, see, due to their velocities, they won't have a tendency to push each other anymore because A is no longer moving faster than B. Okay, when A moves faster than B only, it will push B. Or it should at least try to move faster. Why will it try to move faster? There are no forces acting on A. There's nothing trying to accelerate A. Okay, so due to their velocities, they won't exert a normal force on each other. And these two objects, okay, actually, it may be slightly misleading because of these sponge balls, but assume they are two lumps of clay. Okay, consider one like this. Some deformation has happened, and another one like this. Okay, they got deformed. This is the stage of maximum deformation. These are two lumps of clay now. They have absolutely no tendency to come back to their original shape. Now, if there's no tendency to come back to their original shape, they don't need any space between them. If A tries to become a sphere again, it will need some space here. If B tries to become a sphere again, it will need some space here. So they may push each other in that case. But if they don't have a tendency to get back to their original shape, they don't need space between them. So no normal force will act after maximum deformation. Okay, normal force becomes 0. And if there's no normal force between them, there's nothing to disturb these velocities. So what will happen? These two objects will continue moving with that common velocity. That's all. That is what happens in a perfectly inelastic collision. They will attain a common velocity along the line of impact, and they'll continue moving with that velocity until something else disturbs them. Okay, let's call that common velocity as V. So they'll both be having the same velocity. Now in many books they write that in a perfectly inelastic collision like this one, they write the objects stick to each other. It is wrong to say they stick to each other. Okay, they move together, that's all. They don't actually stick to each other. This point matters in two-dimensional collisions. In a 1D collision, it appears as if they stick to each other, so there is nothing wrong in saying. But in 2D collision, you will see that it is wrong to say that they stick to each other. Okay, so don't use that. Just say they attain a common velocity along the line of impact. They move with a common velocity along the line of impact. Okay, no tendency to restore their original shape. That is what we mean by perfectly inelastic collision. And the last problem that I gave you, I asked you to find out their velocities at maximum deformation. No, I could have asked you the same question this way. I could have said these two objects undergo perfectly inelastic collision, calculate their velocities. Okay, so you have to understand that perfectly inelastic collision means a common velocity along the line of impact. Okay. Let's quickly solve one problem based on this. Assume there are two spheres. Let's say they are moving in opposite directions now. Assume this one is 2 kg. The other one is, let's say, 3 kg. Okay, it's smaller. Maybe it is denser. So even if it is smaller, it can weigh more. Possibility is there. Assume 2 kg sphere is moving with a speed some 20 meters per second. And 3 kg sphere is moving with a speed, say 10 meters per second. Okay, it is given to you that the collision is perfectly inelastic. Perfectly inelastic 1D collision. Calculate their velocities after collision and calculate the loss in kinetic energy due to collision. Do this quickly. Listen, some of you may be having this confusion. Like we know that at a stage of maximum deformation, they'll attain a common velocity. Now the confusion that you might have is whether that velocity will be to the right or to the left. Okay. You can assume whichever direction you want. Fine. You can assume the final common velocity they have is to the left. Write an equation accordingly. If the actual answer is right, you'll get a negative value. If they actually move to the left, you'll get a positive answer. So you can call that final velocity as v and write the equations properly. Okay. If it's actually the left, then v will come out to be a positive value. But if their common velocity is actually to the right, you will get v as a negative value. So you assume whichever direction you want and solve. Okay, I'll just help you visualize the state of maximum deformation. Never mind, we don't have to struggle so much. We will continue solving. (2010). So the gray one will move more, the purple one will move less before they collide. They'll collide somewhere here. I'll write the equation assuming their common velocity is to the left. Let's say they have a common velocity v to the left. Never mind, you can assume it to be right to the right and solve. Nothing wrong in that. I got one answer as 10 meters per second towards left. We'll see. We'll see. Solve it quickly. You only have to apply linear momentum conservation. That one equation will be sufficient. Okay, let us discuss the solution. Yusuf, can you unmute? How much is the initial linear momentum of this system? You have unmuted, but I don't hear anything from your side.
Hello, sir.
Yes. How much is the initial linear momentum of this system?
So 40 for the gray ball.
40 for one of them and
Some 30 for the other balls, 40 ball.
momentum is a vector quantity. You can't just say 40 and 30. You have to assign directions to it.
So like I and J or X and
Okay, which way is the momentum 40 kg meters per second?
so towards the right.
Towards the right. And what is the unit vector
So
to the right? Okay, you can just call it plus 40, okay? So initial momentum of 2 kg sphere is plus 40 kg meter per second. What about momentum of the 3 kg sphere initially?
so minus 30.
Minus 30, correct.
Cap.
Okay, so you can say 40 I cap minus 30 I cap, both I cap only. One is positive I, the other is negative I. So minus 30 kg meter per second. So Yusuf, tell me, how much is the total initial momentum of both the spheres combined?
So 10 kg meter per second.
Right. So the net momentum initially is 10, positive 10 kg meter per second. Finally, I'm assuming both of them to be moving to the left with a velocity v. And they'll have a common velocity v at maximum deformation. And nothing will happen after maximum deformation in a perfectly inelastic collision. So that common velocity is what they will finally have. Aishwarya, you tell me, how should we write an expression for the final momentum? The entire mass 5 kg has a common velocity v to the left. How do we write an expression for the final momentum?
The minus 5 I cap.
Minus 5v I cap. Correct. And then we will equate these two. That's all. Therefore, plus 10, which is the initial momentum, should be equal to minus 5v. You get v as minus 2 meters per second. Vanilla, what does the minus in the final answer signify? What does it mean?
Velocity is towards left.
No, we considered towards left and we got negative answer, means it's actually to the right. Okay, listen all of you, just by looking at the initial values, you can tell how it is going to move. What's the total momentum of this object? 40, positive. Total momentum of this object is minus 30. Which one will dominate? Okay, plus 40 will dominate. So the net momentum of this system is positive, means at maximum deformation, the system will be moving in the positive direction. So directly, just by looking at initial momentum of the individual objects, you can tell how it is going to move at maximum deformation. And after that, you can start solving the problem. Okay, now I took v to the left and I ended up getting a negative answer. What that means is the velocity is actually to the right. Okay, so 2 kg, 3 kg after collision, together they will be moving to the right with a speed of 2 meters per second. Okay, that is the final answer. Next, quickly calculate kinetic energy lost during the collision. Do this quickly, all of you. You should not take so much time for simple calculations. Initial kinetic energy of 2 kg plus initial kinetic energy of 3 kg. Get that? And then final kinetic energy of the 5 kg together. Get it? Subtract. Make it fast. All the speeds and masses are given. Yusuf, how much is 2 kg's initial kinetic energy? Two kg's initial kinetic energy. Rishi? Okay. Formula for kinetic energy is half mv square. So half into 2 into speed is 20, you square it. Everything is in SI unit. So initial kinetic energy of 2 kg is 400 joules. For the 3 kg, half into 3 into 10 square. 10 square is 100. 300 by 2 is 150 joules. So both of them together had an initial kinetic energy of 400 plus 150, 550 joules. Finally, the entire mass of 5 kg is moving with 2 meters per second. So the final kinetic energy will be half into 5 into 2 square. 1, 2 will get cancelled. 5 2 is 10. Final kinetic energy is only 10 joules. So the loss in kinetic energy is 540 joules. Manila, how did you get 240?
So 400 minus 150. No, sir.
Kinetic energy cannot be negative. Kinetic energy is simply half mv. You don't subtract energies. Okay. Kinetic energy, why will you
Okay.
subtract? If two objects are moving, both will have kinetic energy and both of them will contribute to total kinetic energy. Energy is not a vector quantity. Okay. So 540 joules of kinetic energy is lost due to this collision. And because it is a perfectly inelastic collision, the objects are never going, not going to try to get back their original shape. Okay. So if that getting back of original shape doesn't happen, positive work will never happen on this system. During deformation, okay, as I explained using this toy, deformation occurred. During deformation, internal forces will do negative work. If there is any restoration happening, during restoration, internal forces can do positive work because displacement will be outwards. But this is a perfectly inelastic collision, no restoration. And if there's no restoration, no positive work. So this kinetic energy is permanently lost from the system. It could get converted to heat, sound, other forms of energy. Okay. So I'll mention that point also. In a perfectly inelastic collision, negative work is done during deformation but since there is no restoration, no positive work is done. Therefore, the lost kinetic energy, what can you say? It cannot be regained. Okay, it is lost permanently. It is not even stored as potential energy in the system. Okay, you cannot retrieve that energy at all. Okay, so it's lost permanently. Fine. So this is what happens in a perfectly inelastic collision. Once the objects undergo maximum deformation, that means once they attain a common velocity along the line of impact, nothing happens after that. Okay, no restoration, so no further disturbance at all. There are two other types of collisions. The second one is partially inelastic. Partially inelastic means partial restoration of shape is going to happen. Not complete restoration, but partial restoration. Now, in that case, what will happen if these two objects which have undergone a collision want to get back their original shape? Okay, you look at what I'm drawing in the first diagram, in the first picture. If the objects want to get back their original shape, they need some space between them. So they'll continue pushing each other. So in a partially inelastic collision, which is what we'll discuss next, and also perfectly elastic collision. So when there is partial restoration or complete restoration, some more pushing will happen after maximum deformation. And if some more pushing happens, B's velocity will increase further, A's velocity will decrease further, the objects will move separately after collision. They won't move together like this. Okay, they'll have different velocities, unequal velocities after collision. Okay, so partially inelastic and elastic collision, perfectly elastic collisions, those we'll discuss in tomorrow's class. So let's quickly go through what we discussed today. So this is the main thing from this lecture, the stages of collision. Initially the objects are separate, but the moment they come into contact, normal force starts acting between them. And as why does normal force act? Because one object tries to move faster than the other, it will push. Okay, so A will push B, B will also exert a normal force on A. Due to that, deformation will happen. During deformation, internal forces will do negative work. So during this process of deformation, some loss in kinetic energy is compulsory. Irrespective of nature of material, loss in kinetic energy during deformation is must. And when will deformation stop? When the two objects attain a common velocity along line of impact, deformation stops. After that, there may be restoration, may not be restoration. They'll have to tell you that in the question. Okay, based on that, we have three different types of collisions. One collision in which there's no restoration at all, that's called perfectly inelastic, which is what we discussed today. Partial restoration is partially inelastic. Complete restoration is said to be fully elastic. Okay. We'll discuss those cases in the next class. Okay, thank you all. We'll continue tomorrow.
So can you send today's note once?
Okay.